This video is the first in a series to teach the principles of our physical existence as presented in my book, Are We Just Bubbles? An Alternate View of Existence. Now, a good place to start is always at the beginning. So I will begin with the physical existence of space. Even though we can't see it, we can't see anything in the empty space between us here on this earth, we know that it's not really empty. We breathe the air that fills this space. We can feel the force and movement of air in the wind. The air physically exists even though we can't see it. In the same way, universe space exists and is a physical part of the universe even though we can't see it. In the vacuum interstellar space in our galaxy and vast regions of intergalactic space within our universe, there is a real and physical space existing even though we can't see it. We know that space exists because electromagnetic energy, gravitational fields, and the like exist in it. Our universe space has bounds, or in other terms, it is finite. It doesn't go on forever. At the space boundary of our universe is an infinite void, an abyss where absolutely nothing within our physical capabilities to detect exists. There is no time, energy, or forces of any kind that we could detect outside of our universe. Our universe consists of a finite set of space bubbles, both vacuum space bubbles and space bubbles that are compacted to form matter. Finite means that there's only a certain amount of them. When the universe first began, these bubbles were extremely tiny by our standards. Each bubble has a source of new space material within it. And as the space pours in from outside of our universe, from the blackness of the abyss, our universe expands. We cannot see this expansion because we, along with the bubbles, are expanding. We are made of these bubbles. And all of space is made of these bubbles. There is no light, no electromagnetic energy, no gravity, or anything outside of our universe boundaries. This idea might give some of you a touch of heartburn because we have always thought space was emptiness and it didn't consist of anything. But this philosophy comes from the primitive notion that it doesn't exist physically if we can't detect its existence with our senses. These types of things were thought to be spirits before we became enlightened. But like the invisible air, there are indications that empty space is physical because it interacts predictably with other physical things that we can see, and that it is not a spirit acting with its own will. We know that there is a connection between space and time, as predicted by Einstein. We have seen that the speed of an object through empty space can affect the passage of time in that space. And inertial force and gravity can affect objects in empty space. Electric and magnetic forces are transmitted through space between objects. Even though we can't see anything in vacuum space, we know that there is something there because things exist in it. Things like electric forces, magnetic forces, gravity, and inertia. Now this is in air, but the same thing would happen if we were out in space. I'm going to demonstrate how electric force can travel through space and cause repulsion. The little ball of aluminum is being repelled by the charge that's transferred to it on the globe when it touches it. And so it forces it away from the sphere. Likewise, magnetic fields can exist in vacuum space and act on pieces of matter. For instance, this magnet is attracted to this steel screwdriver through space. This will happen whether it's in air or in a vacuum. These actions in empty space are indication that space is physical and these forces are not the actions of some invisible spirit. So if it physically exists, but we can't see it, what's it made of? Now this answer is probably going to shock you. But vacuum space is made of invisible space bubbles. As a matter of fact, everything physical in the universe is made of space bubbles too. Let that sink in for a minute. Everything in our physical reality consists of invisible space bubbles. You could think of these bubbles as a foam, all of empty space. The empty space between the stars and the galaxies. Empty space between atoms. The space inside of a solid between the electrons in the atoms. And even between the components of an electron and the tiniest subatomic particles in the nucleus of an atom. These spaces are all composed of vacuum space bubbles. The solid subatomic particles of an atom, the ones we can detect, are composed of compacted space bubbles. The fact that they are compacted and denser than the vacuum space bubbles is what makes them visible to us as matter, and they have properties of mass. In the last few decades, scientists of the world have been on a quest to find the ultimate component of the universe. Leon Lederman called it the God particle. Some have named it the Higgs boson. In order to see if it really exists, scientists of the world, in a multinational effort, have built a $9 billion atom smasher in Switzerland called a Large Hadron Collider. It is the largest machine in the world. It is donut-shaped, is 16.7 miles in circumference, and is buried 600 feet deep in a tunnel underground. It is used to accelerate two streams of charged particles going in opposite directions almost at the speed of light. Now these particles are very small, mostly protons, but they accelerate them to almost the speed of light. And then they smash them together to see what flies out. Now according to some scientists, God particles supposedly pop in and out of existence from absolutely nothing. So it might be a problem to detect their existence from the shards of a collision. It's sort of like smashing a rock with a giant hammer and trying to figure out what the rock was made of by looking at the dust and shrapnel flying out of it. According to what I believe and propose in my book, scientists will never see a God particle. This is because what they are looking for is an invisible vacuum space bubble. They do exist and envelop all of our universe. But there is nothing in our universe that will allow us to see them directly. We can only anticipate their presence by the actions we can see on matter, which is also composed of space bubbles, although they are compacted. Okay, this is probably enough on this space bubble foam. The point I wanted to make is that space as we know it consists of vacuum space bubbles. Then you might wonder, what are the bubbles made of? Well, it turns out that each bubble is made of its own unique universe space that it cannot share with its neighbor. Kind of like people. Each little bubble is unique and individual and has a creative source within it that is continually making its own new space material and causing the bubble to expand against its neighbors. Remember that it can't share its space with its neighbors, so it expands right up to the face of its neighbor and forms a barrier there out of its own material. Where does this new space material come from? It comes from a creative source outside of our universe reality and is unknown to us. Something outside of our universe, in the abyss or whatever you want to call it, is pouring new universe space into each of the space bubbles. You might want to think that this source is God or a creator. Others and some scientists would rather think that it comes from nothing rather than from a creator. But in any case, we can't ever know for sure because it is outside the bounds of our reality. I want to give you a visual representation of what the space bubbles expanding would look like. So I've obtained a series of little balloons with these stems that can fill into each one of them individually. And this is what happens in the case of the vacuum space bubbles. As the space pours in from the outside of the universe into the inside of the bubbles, each bubble expands against its neighbor. And in this way, the universe is expanding invisibly into the abyss. The first thing we have to do when we make a measurement is to assume that the object we are going to measure is finite. That is, it has a certain length, a beginning and an end, and that it is constant, not changing in length while we're trying to measure it. Then we take another finite and constant object that was set up as a measurement standard, a ruler for instance, and compare that to the length of the object being measured. The comparison is done in the form of a ratio of the object length to the standard length. So we take this pencil and this ruler, we find the beginning of the pencil, we put that on the 0 part of the ruler, and then we go over here to this end and see where it comes to, and we see that it's 6 1/2 inches long. Okay, what does that really mean? That means that there are 6, this is the unit of measurement, which is an inch, and we have multiples of this. We have multiples of this inch on the ruler, and we have fractional portions of an inch in between. So we can directly read off the ratio of the standard length, which is 1 inch, to the length of the pencil, the ratio. So there's 6 1/2 over 1 pencil length. That's the ratio. Both portions of both portions of space that's in this pencil and in the ruler are composed of space bubbles, and they're considered constant and not changing. So what we are really doing is comparing two portions of universe space against one another. What this really means is that the number of space bubbles along a line in the measurement standard and the number of bubbles in the line in the object being measured is not changing while the comparison is being made. Now, to better demonstrate that, I'm going to use something else here. Our vacuum space is really three-dimensional. That means it has length, width, and depth. But in order to show how measurements are made and how they remain constant with universe expansion, I'm using a two-dimensional representation of space. It'll work the same way. It just makes it easier to see. So this is actually a cross-section of our 3D vacuum space. Now in vacuum space, all of the vacuum space bubbles are the same size and have the same sides in their bubbles, and they're all flat. So that's why these are shown as squares. Each little dot in one of these bubbles here represents a creative source that can generate new vacuum space. And now I have a representation of some objects that we can see in our vacuum space. Now the condition for an object to have mass and to be seen in our universe, it has to have a density greater than that of the vacuum space bubbles. So these are the vacuum space bubbles here, and these objects here consist of space bubbles that are compacted. There are 2 space bubbles per vacuum space bubble in these 2 objects here. So we would be able to see them in our vacuum space. Now pretend they're sitting out in the vacuum of our universe, and we want to measure that with a ruler that we have. So here's a ruler, and we're going to measure center to center between these 2 objects. Now remember that our ruler is also made of vacuum space bubbles and space bubbles, compacted space bubbles. So these, I've shown this down here on the bottom, there are these space bubbles in a line along the ruler. Would be the same as the vacuum space bubbles that we have in space. The distance here can be thought of as a certain number of vacuum space bubbles between 2 points in space. And what we're doing then when we measure something is we're comparing the number of space bubbles in our ruler to the number of space bubbles of the distance that we're measuring between these 2 objects. So that's what we're talking about, it being a ratio. It's a ratio of the number of units here to the number of space bubbles between the 2 objects. Now, in reality, the ruler has compacted space particles, and these objects here have compacted space particles, but it doesn't matter. What we're looking at is the number of space bubbles between the 2 objects, which we could look up here and see and count this number, and if we looked in our ruler, we'd see that they're the same. So we're assuming when we make a measurement that these are the space bubbles, vacuum space bubbles in the ruler and in our vacuum space are constant and unchanging to us. So we would measure then that's a representation of the number of bubbles. Now supposing some time passed and our space expanded into the abyss, or vacuum space. And we're going to take another measurement now after some time passes. We can see that the vacuum space bubbles have grown in size from what they were. Our objects have grown in size from what they were. And the compacted particles have grown in proportion to the space bubbles. Now, we're going to look at our new ruler, which also has the same representation of vacuum space bubbles as our vacuum space. We measure it again, and we see that it's 3 1/4 units between the two objects, just like it was before. We can't tell that our space has expanded into the abyss, because everything expands with time, including us. But now, let's use our imagination and step outside the universe. Let's say we could do that and we could see these vacuum space bubbles and our universe vacuum space in the abyss. We're stepping outside of it. We can do that in our minds. We can't do it physically. If we do that, though, we're going to have something to measure it with. And about the only thing we can use is the initial size of the universe when it came into existence. I've made this ruler here. This ruler here uses the initial size of the universe in the abyss when it came into existence as a standard unit. And so that does not change when the universe changes. When we look at distance with this ruler, we're comparing its current size to its initial size. And so we will be able to see the universe expand into the abyss with this ruler. So if we looked at the first instance that I had with this ruler, we see that it would measure 6 3/4 between the two objects at this point in time. And then sometime later, we look at it again, and since this ruler doesn't change, we see that the universe has expanded quite a bit. It's now 13 1/2 units between the two objects, even though it read 3 1/4 in both instances from inside of the universe. We cannot see that expansion because the objects and the measuring standards are expanding along with our space bubbles, which they're also made of. The number of bubbles between measured objects remains constant, so the distance appears to be constant to us. So this pretty much concludes this session. Here's what we've discovered in this session. Everything in our universe consists of invisible expanding space bubbles. Compacted groups of these space bubbles become visible matter and have properties of mass. Measurements that we make are just a comparative ratio of two portions of space, one being a measurement standard that is considered to be constant. The ratio is really a comparison of the number of space bubbles in a line between 2 points in universe space. Each bubble is unique in that it cannot share space with any other bubble. The boundaries of each bubble are made of its own unique material, and it has a creative source within it that makes it expand against the boundaries of its neighboring particles. There are no voids of non-universe space between the bubbles. Therefore, they are not round. They have flat sides that terminate on each other. The vacuum space bubbles, which are the biggest and fastest expanding, are cubes. All of the rest, the compacted bubbles, can be any kind of geometric shape, solid geometry shape you can think of. They can have irregular sides and everything else. But the vacuum space bubbles are cubes because they have to be symmetrical from all directions. Vacuum space bubbles and compacted groups of bubbles are invisibly expanding into the infinite void of non-universe space. This type of expansion, which is like bread dough rising everywhere from within, isn't strictly invisible to us. We have to see that in our imagination. These bubbles can only expand. There is nothing in the universe that can uncreate space. Nothing can force it back to where it came from. The expanding universe that we can see is not the same as this invisible expansion. Instead, it is caused by actual movement of bodies of matter within the vacuum space bubbles. The apparent compression of space, as we might observe in a black hole, is the result of that space expansion slowing down while we and our surrounding space continues to expand at a faster rate. It looks like it's shrinking, but it's just staying the same size and we're expanding. Just like when we took that abyss ruler and looked at the universe, if something didn't expand, it would stay the same size on that ruler. To us, it would look like it was shrinking, but in actuality, it was just staying the same and we were expanding. This concludes session 1 of the Are We Just Bubbles tutorial. In session 2, we will discuss the beginning of the universe, time and energy as it relates to the expansion of space bubbles. Thank you very much for listening.